Hello friends, so far I have discussed about pure or intrinsic semiconductors. Certain impurities can significantly improve electrical properties of semiconductors. For example, one boron atom added in 10 power 5 silicon atoms can increase the conductivity of pure silicon by a factor of 10 power 3 at room temperature. Deliberate addition of impurities to a semiconductor is called doping. In this lecture, I am going to discuss about doped semiconductors. First, let us consider doping of an impurity atom of valence 5 like phosphorus and arsenic in silicon which has 4 valence electrons. We know that silicon has a diamond cubic crystal structure. Each silicon atom has a coordination number of 4. Each atom forms 4 covalent bonds, one with each of its nearest neighbors, as shown schematically in this diagram. The impurity atom substitutes a silicon atom in the lattice. It has been confirmed by lattice constant studies that the pentavalent impurities enter the lattice site by substituting a silicon atom, and such impurities do not enter interstitial positions. A pentavalent phosphorus atom forms 4 covalent bonds with 4 nearest silicon neighbors, and 1 extra valence electron of the pentavalent impurity is left over. The pentavalent impurity is called a donor because it can donate the leftover electron, which can be excited to the conduction band and which can take part in electrical conduction process. At very low temperature, the excess electron remain bound to the phosphorus atom. At sufficiently high temperature, the excess electron breaks free, leaving behind a positively charged phosphorus atom. However, the crystal remains neutral as a whole because the excess electron remains in the crystal. The whole process is known as the thermal ionization of the impurity atom. Let us now try to estimate ionization energy using Bohr theory of hydrogen atom. The Coulomb potential between P plus and the electron is not the bare Coulomb potential. Due to screening, bare Coulomb potential E square by R is reduced by a factor of 1 by epsilon, where epsilon is the static dielectric constant of the medium in a covalent crystal. The factor 1 by epsilon takes into account the reduction of Coulomb force between charges due to the electronic polarization of the medium. Free electron mass is replaced with effective mass Me star. Now, let me show you how to get ionization energy and Bohr radius for a donor atom using Bohr theory of hydrogen atom. From Bohr theory, ionization energy of atomic hydrogen is equal to e to the power 4 m divided by 2 h bar square, which is equal to 13.6 electron volt. In semiconductor crystal, replace E square by E square divided by epsilon. This is because the Coulomb potential is reduced by a factor of 1 by epsilon due to the screening in a semiconductor crystal. We also have to replace free electron mass by effective mass of an electron. Then we can rewrite this equation to get the expression for ionization energy of donors. ED is equals to, so in place of E square, I am going to replace E square by epsilon such that I get e to the power 4 divided by epsilon square, and then in place of m, I am going to replace me star, and then we have this factor 2 h bar square. Now this equation we can rewrite as e power 4 by 2 h bar square is equals to 13.6 divided by m. And then if we replace this term in this equation, then we get 13.6 divided by epsilon square times me star by m. Bore radius of the ground state of hydrogen atom is given by h bar square divided by m times e square, which is equal to 0.53 angstrom. Again, we have to replace e square by e square divided by epsilon, and we have to replace m by me star. And if we do that, then we get the Bohr radius of the donor atom to be AD is equals to epsilon times h bar square divided by me star times e square, which is equal to 0.53 epsilon divided by me star divided by m angstrom. Note that I have used this equation to write this step. Now let me get some rough estimate for real semiconductors like silicon and germanium. In case of silicon, epsilon is equals to 11.7 and me star is equals to 0.2 m. There is some complication because the effective mass in silicon is not isotropic, but this is good enough to get some rough estimate. So for silicon, ED is equals to 13.6 divided by 11.7 whole square, which is the value of epsilon, times 0.2, which is the value of effective mass. And this is roughly equal to 20 milli electron volt. Similarly, for silicon, the Bohr radius is AD is equals to 0.53 times epsilon is 11.7 divided by effective mass is 0.2. And this is approximately equal to 31 angstrom. Let me do the same exercise for germanium. In case of germanium, epsilon is equals to 15.8 and Me star is equals to 0.1 times the free electron mass. Thus, for germanium, Ed is equals to 13.6 divided by epsilon square. Epsilon square is 15.8 square times the effective mass, which is 0.1. And this is approximately equal to 5 milli-electron volt. And the Bohr radius is equals to 0.53 times epsilon is 15.8 divided by the effective mass, which is 0.1. And this is approximately equal to 84 angstrom. A donor impurity atom has one excess electron, which is weakly bound to the donor impurity. We have estimated the ionization energy of the donor atom from Bohr theory of hydrogen atom. Ionization energy of hydrogen atom is 13.6 electron volt. Donor ionization energy reduces by a factor of Me star divided by M times epsilon square. In a semiconductor crystal like silicon or germanium, this factor is almost 10 power minus 3. Such a spectacular decrease is because of the fact that Coulomb force between the positively charged impurity atom and the electron reduces in a semiconductor crystal because of screening. As the Coulomb attraction is reduced inside a semiconductor crystal, the ionization energy also reduces. Donor ionization energy is very low in silicon or germanium. It is of the order of thermal energy at room temperature. Thus, at room temperature, thermal energy is sufficient to free the weakly bound electron from the positively charged donor impurity. Such free electron takes part in electronic conduction process. This is the broken bond model of semiconductor, where an electron breaks free from its native atom and can move around like free electrons in a crystal. The weakly bound electron is orbiting around the positively charged donor impurity. We also have estimated the Bohr radius of the weakly bound electron using Bohr theory of hydrogen atom. Bohr radius in hydrogen atom is 0.53 angstrom. For a donor atom in silicon or germanium, it increases by a factor of epsilon times M divided by Me star. This factor is almost 10 power 2 in silicon or germanium. This is again due to the reduced Coulomb force between the positively charged impurity atom and the electron. In silicon or germanium, Bohr radius is very large. Bohr radius is so large that donor orbits overlap at relatively low donor concentration compared to the number of host atoms. Bohr radius of donor in silicon and germanium is very large. As a result, donor orbits overlap at relatively low donor concentration. Because of appreciable overlap of the donor orbits, an impurity band is formed from the donor states. Donor levels generally lie very close to the conduction band edge. Conduction can happen via two routes. Number one, ionizing a donor creates a free electron in the conduction band. And this free electron can take part in electrical conduction. Number two, conduction in impurity band via electron hopping from donor to donor. Note that it is easier for a donor electron to hop to an ionized or unoccupied donor level than to an occupied donor level, such that two electrons need not occupy the same site during charge transport. Thus, some donor atoms need to be ionized before donor-to-donor electron hopping can start. Thermal ionization is one possibility. Another possibility is presence of some acceptor impurity such that some of the donors are always ionized, even at very low temperature. Let us consider a semiconductor doped with donor impurity. For example, silicon doped with phosphorus. Such a semiconductor is known as N-type semiconductor because it has more electrons than holes. Remember that having more electrons than holes is only possible in an extrinsic semiconductor. In an intrinsic or pure semiconductor, number of electrons is always equal to the number of holes. Say in a phosphorus doped silicon, total number of free electrons in the conduction band is equal to N at some finite temperature. Some of the electrons in the conduction band are created by thermal ionization of the donors, as shown by purple arrows in this diagram. Rest are excited from the valence bands, as shown by the red arrow in this diagram. Let's assume P is the number of holes in the valence band, which is equal to number of electrons excited from the valence band. Then electrons from donor level delta N is equals to N, which is the total number of free electrons, minus P, which is the number of electrons excited from the valence band. And we can write P is equals to N minus delta N. Now we apply law of mass action. That is N times P is equals to Ni square, where Ni is intrinsic carrier concentration. Now we replace P equal to N minus delta N in this equation such that N times N minus delta N is equals to Ni square, which can be written as N square minus delta N times N minus Ni square is equals to 0. So we have to solve this equation. Solving this equation, we get N is equals to delta N plus square root of delta N square plus 4 Ni square divided by 2. Now let us assume complete thermal ionization. That is delta N is equals to ND, where ND is the donor concentration. Thus, we get N is equals to ND plus square root of ND square plus 4 Ni square divided by 2. Now, if we consider very heavy doping, then the donor concentration is much larger than the intrinsic carrier concentration. In that case, contribution from the intrinsic part is negligible, and we can write as N almost entirely coming from the donor atoms. Instead of pentavalent impurity, if we dope silicon or germanium with trivalent impurity, we get p-type extrinsic semiconductor. Example of p-type dopants are boron and aluminium. When a boron atom substitutes a silicon atom in the lattice, it has one bonding electron missing. That is, a hole is attached to the boron atom. At finite temperature, electron from adjacent silicon can jump to fill the void. As a result, the hole becomes free from the parent boron atom and is available for conduction process. In band picture, holes jump from impurity to valence band at finite temperature. Boron and aluminium are known as acceptor atoms because they accept electron from valence band to complete the covalent bond with neighboring atoms, leaving holes in the band. Similar to the electrons, Bohr model applies for holes as well. In general, one can dope a semiconductor both with donor and acceptor impurities. Ionization energy of both donors and acceptors are comparable. Thus, at a given temperature, both donor and acceptor impurities will be ionized at the same rate. If number of donors dominate, we get N-type semiconductor. On the other hand, if number of acceptors dominate, we get P-type semiconductor. Electrical conductivity sigma is equals to N E mu E plus P E mu H, where N is the concentration of electrons and P is the concentration of holes. Mu E is the mobility of electron and mu H is the mobility of holes. We know that mobility depends on temperature by some modest power law. As a result, temperature dependence of conductivity is dominated by exponential temperature dependence of carrier concentration, which is proportional to e power minus delta E by kBT, where delta E is of the order of Eg, that is band gap in case of intrinsic semiconductors. In case of extrinsic semiconductors, delta E is of the order of Ec minus Ed, where Ec is the conduction band minimum and Ed is the donor impurity level. As a result, log sigma versus 1 by T plot is linear, having two different slopes for the extrinsic and intrinsic region.